Okay, for this video, we'll be going through your practice paper for your WA2. Okay, so let's start. Some of the questions have been taken out, like static electricity, because it's not really in our syllabus anymore. So we'll just do what we have for our on the paper, right? So for the first question, an ammeter records a reading of 4 ampere. So this is my current I. They want us to determine the number of charges that pass through the ammeter in 3 minutes. So this is definitely time, and this is our charge Q. Okay, so the trick here is that the time is given in minutes. So this is a SI unit formula. So we need to change it to SI unit, which is 3 times 60, 180 seconds, okay, for our time. So we apply the formula Q equals IT, and since we have current, which is 4, and time is 180, the number of charges that flow through in 3 minutes is 720 coulomb. So answer is D. Okay. Next, the work done by a battery to drive a charge of 5 coulomb. So this is my Q. So this work done is actually 10 joules. So this is W. Determine the electromotive force. So it is this symbol. So we have this symbol, electromotive force equals to work done over charge. So since we have work done 10 joules, charge is 5, the EMF will be 2.0 volts. So answer is B. Okay. Now the question 4, the diagram shows an incomplete circuit. What should be connected in the dotted box so that the brightness of the bulb can be adjusted? So the answer will be rheostat. Because what is rheostat? It is a variable resistor. So what's the function of the rheostat? Okay, being a variable resistor, it is able to we are able to control the amount of resistance, right? And because V equals to IR, so simply the current can tell us whether the bulb will be brighter or less bright. And because our V is fixed, and if we add a resistor in series, we are actually able to control the resistance. So if I want the current to be more, I want the light bulb to be brighter, right? So my resistance, I can adjust it, okay, to be lower. Okay, question 5. What is the effective resistance of the resistors in parallel? Okay, so because they are in parallel, right? So we can actually use this formula, 1 over REFF equals to 1 over 2 plus 1 over 4 plus 1 over 6. Okay, then you need to remember to flip. So this is 12 6 plus 3 plus 2. So we get 11 over 12. Okay, but we need to flip it, right? Because this is 1 over REFF, so we flip the fractions on both sides. We'll get 11 over 12. We flip it, we'll get answer of B, 1.09 ohms. Okay, what's the effective resistance of the resistor shown below? So if we role play current is going to come to this place and then split up. That means there's going to be a parallel branch over here. Okay, parallel circuit. And then after that, the current is going to meet up over here and then combine. So basically, this whole thing is in series with the 2 ohm. That means we have to try to solve the parallel circuit part first. So imagine you have a current, you come over here, okay, you split up. So current 1 and current 2. So for current 1, it actually experiences 2 resistors, the 5 ohm and the 4 ohm, one after another. That means they are actually in parallel. So I can, in series, okay. So I say again, current I1 actually experiences 5 ohm and 4 ohm resistors one after another. That means it is series. So for series, we can actually add up the resistance. Okay, so I don't do anything to the 3 ohm below. I also don't do anything to the 2 ohm. So now, the 9 ohm and the 3 ohm are actually in parallel. So let us solve it first. So we get let me do my math. 9 and 3 is actually, you will get 27 over 12. okay, and 2 ohm. So 27 over 12 is 9 over 4. Okay, so we'll get the answer will be D, because after that we can actually add them up. Okay, so please bring your calculator for the WA. Okay, question 7, circuit below is used to measure the resistance of resistor R, which is this one. Okay, so if R is found to be 3 ohm, what will be the reading of the voltmeter and ammeter? So if this is 3 ohm and this is also 3 ohm and there's no other resistor, right? So basically we can turn them into 6 ohm, 24 volts. So with this we can actually find the current. So V equals to IR, so I equals to 24 over 6, so we get 4 ampere. And because this is a series connection, right, just by considering the resistors, in a series circuit, the current is the same. So I'm going to say the current flowing through the ammeter is 4 ampere. Okay, so we put in this 4 ampere. So the trick here now is the voltmeter is actually measuring the potential difference between this second resistor. Okay, so we have a current of 4 ampere passing through this resistor, right? So the voltage measured by the voltmeter, it is the current multiplied by the resistance, we get 12 volts. So answer is 12. Okay, so answer is B. How about the potential difference across this? It's also going to be 12 volts as it has the same resistance, okay, of 3 ohm, and it also has the same current of 4 ampere. Then we find that if we add up the 12 volts and the 12 volts, it is equal to the EMF, which means to say in series the potential difference is the sum. You sum them up, it will be equals to the EMF. Okay, question 8 is your R equals to rho L over A. So I have a wire of length 4 meters, L1, with a cross-sectional area of 0.2 mm square, I call it A1, and a resistance of 2 ohm. Which wire of the same material? And if you recall, the formula is R equals to rho L over A. The rho is for the resistivity. Okay, and because they are the same material, they will have the same resistivity, so we don't need to think about what is the resistivity. Okay, so they ask which wire has also a resistance of 2 ohm. Okay, so let's take a look. That means they are going to have the same resistance. That means R1 should be equals to R2. Now if we make R the subject of the formula, it is actually length over R equals to rho L over A, so I don't need to do anything. Okay, R is already the same for both wires, R1 equals to R2, but I'm going to make resistivity length 1 over A1 to be equals to resistivity 2 length 2 over A2, because R1 is equals to R2 and R1 is this, R2 is this. Now resistivity is the same, so I can cancel it. Okay, length 1 is 0.4, area is 0.2. Okay, so I need to get the same ratio of L2 over A2. So I have to use I have to check every option. If you look at option A, I'm not going to get this ratio of 2. Okay, you look at option B, I'm also not getting it. You look at option C, yes, because it's 0.8 over 0.4, and then I get a resistance of 2. So C is the answer. For D, you're not going to get it. Get a factor of 2 as well. Okay, question 9. A 10 ohm resistance wire AB is connected in a circuit as shown. Given that the resistance wire is 2 meter long, what is the reading on the voltmeter when the jockey is at point C? Okay, it's at point C. So this voltmeter is actually measuring this resistance wire of length 1.6 meters. The whole wire is 2 meters. The whole wire is 2 meters. So it's like equivalent to say that this is 1.6 ohm and this is 0.4 ohm. If we treat the length of the wire 2 meters as 2 ohm. Okay, just a simple representation, right? So if it's 1.6 ohm and 0.4 ohm, their total resistance is actually equals to 2 ohm, which is like the whole length of the wire of 2 meters. Okay, so let us maybe just use these dummy numbers. Okay, and we can get, let's say example, this resistance wire is 2 ohm. Okay, therefore the current will be 6 ampere. Okay, if it's 6 ampere, that means I'm going to have 6 ampere passing through this 1.6 ohm. And because V equals IR, my V is going to be 6 times 1.6. So I'm going to get 9.6 volts, which is the answer. But let us check. How about for this 0.4 ohm? I'm also going to get 6 ampere passing through it because it is a series circuit. Okay, it's just that the voltmeter is connected across this 1.6 ohm, which is actually what I propose as the 1.6 meter wire lah. So the V is going to be 6 ampere in series. The current is the same, multiplied by the resistance, I get 2.4 volts. So if you add up this, you are equal to 12 volts because in series, the voltage or the potential difference is the sum. The sum is equal to the EMF. Okay, let's go to section B. Figure 3.1 shows an electrical circuit containing a resistor of resistance 60 ohm, which is this guy, and a light bulb of 40 ohm. The cell in the circuit has an EMF of 24 volts here. State what is meant by the potential difference across the light bulb. Yeah. Let me just copy the answer. Okay, it is actually the work done to drive a unit charge through the light bulb, right? So that is the definition for potential difference. And I'm using the context of light bulb. Next, when the switch is open, determine the effective resistance of the circuit. So it's best to redraw the circuit. I'm going to redraw it here very quickly. 24 volts, right? So I have 60 ohm. And because switch is open, so I can just ignore. I can directly connect it to the 40 ohm. And then this is my circuit. Okay, so the effective resistance is actually 100 ohm. And when this switch is open, I'm going to still continue using this circuit. What is the ammeter reading of A1 and A2? Okay, so if you recall, ammeter A1 is connected after the light bulb, and ammeter A2 is on the main branch. Okay, when we have two branches here. But because this branch is out, right, it is an open circuit, so current will not flow through it. So actually A1 will be here, A2 will be here. And therefore, I can say that A1 is equals to A2 because the current in a series circuit is the same. So I need to take V equals IR. The total, the voltage is 24. The current is unknown. The total resistance is actually 100 ohm. So my current is going to be 0.240 ampere. Okay, 0.240 ampere. And it is equal for both because they now form a series circuit. Now calculate the potential difference across the light bulb. We use V equals IR. Actually, this WA, we did a lot of this. The current flowing through is 0.24. The resistance of the light bulb is 40. So therefore, you multiply them together, you will get 9.60 volts. Okay. Now, when the switch is closed, determine the effective resistance of the circuit. So now I'm going to have to redraw the circuit with the switch closed. Okay. So you find that actually when the switch is closed, right, there is no resistance over it. Right. This is the part whereby the switch is closed. And over here, I have 40 ampere, my light bulb, and A1. Okay. Then I have A2 over here. When this switch is closed, it presents itself as a short circuit. Okay, so this is a very special case. right, this path actually has no resistance, which means all the current will actually just choose to go to this path. No current will be flowing in this path, so I can then cancel this out, right? Because the current are like human, they see that this path, the top path actually has no resistance, and definitely all the current will flow through that path, which means the effective the circuit will actually now look like this. I'm going to omit the lower path because the top path presents itself as a shortcut, so I left with A2. Okay, my light bulb and A1 is out of the picture because of this short circuit. So determine the effective resistance, we have only this 60 ohm left. Okay, then they want us to calculate the or determine the ammeter reading A2. So again, we use V equals IR. So please, for your formula V equals IR, make sure that you memorize it as V equals IR. Okay, and learn how to apply. So my current, because my effective resistance is now 60, my current is 24 over 60. So equals to 0.400 ampere. You find that this current is actually higher than before that. Okay, because now we have lesser resistance. Alright, and so this will be the video for practice paper 1. I'll be doing practice paper 2, which mainly focuses on light.